Hi everybody. Up to this point in the course, Charles and I have presented already a lot of material, which included both material that can be found in traditional quantum mechanical textbooks and also some non-standard exposure to quantum physics. For example, superconductivity, path integrals, some elements of quantum localization, etc., etc. And I have to say that on my side, the preference has been for the latter. I wanted to tell you more about things that you cannot find in traditional textbooks. But today is certainly going to be an exception, because today I'm going to present a very traditional quantum mechanical problem that no reasonable quantum mechanical course can avoid. And this is the problem of a harmonic oscillator. So the reason I cannot avoid this problem is twofold. So first of all, a quantum harmonic oscillator, the problem of quantum harmonic oscillator is relevant to a variety of various experimental systems, ranging from cold atoms where atoms are trapped in a quadratic potential to, let's say, molecules whose low energy oscillations are described by harmonic oscillator, to quantization of light, to quantization of oscillations in crystals, so-called phonons. We're going to actually discuss them soon, and many other things. And second, so the problem on the theoretical side, the solution to the problem of harmonic oscillator is very illuminating and useful in that it gives you very useful tools, so-called creation and annihilation operators that are useful in a variety of contexts across various fields of physics. And you're going to see these things very often in other courses if you pursue physics studies. But before solving the quantum harmonic oscillator problem, let me remind you the story behind the classical harmonic oscillator. And here I have an example of a classical system which exhibits these small oscillations near an equilibrium position, and these oscillations exactly are the harmonic oscillator motion. So on the mathematical side, what happens here, of course, is that the mass here experiences the so-called Hooke's force, which is proportional to the displacement x of the spring relative to its equilibrium position. So let's say here, this is my x-axis, and let's say we have an equilibrium position somewhere here, so this is my 0. So this is x, and the force is proportional to this displacement, and in this case, at this moment of time, it's this Hooke's force x in this direction, in the negative x direction. Now, I can write this force, of course, as a minus gradient. In this case, it's just one-dimensional gradient, or just the derivative with respect to x of some potential. And to produce a linear force, of course, I need to differentiate a quadratic potential. So in this case, it's kx squared over 2. And this is exactly the potential energy of a harmonic oscillator that eventually is going to appear in our Schrödinger equation in the quantum version of this problem. Now, on the classical side, though, what I have to do is I have to solve the second Newton law presented here. So, and the second Newton law, of course, is just mass times acceleration. The second derivative of x is equal to all the forces. In this case, there is just one force. In this example, let's see if we ignore gravity, which is not going to modify it too much. But in this case, it's going to be just one force, which is the force due to the Hooke's law. And if I write this equation, if I divide this equation by m, and instead of writing the second derivative, I will write it in the compact form, x with 2 dots on top. So I can write it as x 2 dots plus omega squared x is equal to 0, where omega is equal to the square root of k over m. And a solution to this differential equation is sines or cosines with some arbitrary phases, and it's up to us which solution to choose. So there will be some amplitude here, so we can choose a sine or we can choose a cosine. And as long as we have two free parameters which will determine the initial conditions, the initial position and the initial velocity, these are all general solutions of this classical problem. So let me choose, for example, the sine solution and present it here. So this is the solution to this harmonic oscillator. Now, to move further, let me choose a particular initial condition which I can do, which corresponds to x of t equals 0 being 0. So let's say the initial moment of time at the position of our harmonic oscillator was exactly at the equilibrium point, just for simplicity. And in this case, this is my solution. Now, if I want to find the velocity of the oscillator as a function of time, so all I have to do is to differentiate the position, and in this case it's going to be just x naught, some amplitude of the oscillations, times omega times cosine of omega t. So what I can do now, I can write the energy of the system, which is not a function of time, as we shall see in accordance with the conservation law, which would be a sum of the kinetic energy mv squared over 2 and the potential energy v of x, which is equal to 1/2 kx squared. K is the coefficient in the Hooke's law, or expressing it through the mass and frequency, I can write it as so, 1/2 m omega squared x squared. And this is, by the way, the form in which it typically appears in the literature, in particular in quantum mechanical literature. So now indeed, if we plug in this result into the energy, so the energy is going to be equal to mv squared over 2, so we're going to have m over 2 x naught squared omega squared plus cosine squared of omega t from this velocity term, and potential energy plus m over 2 x squared x naught squared omega squared from here, sine squared of omega t. And then we can use the fact that cosine squared of an arbitrary angle plus sine squared of the same angle is equal to 1. And so we see that indeed the energy is simply this. So, and the energy is conserved, indeed in accordance with the energy conservation law. But of course, even though the energy E here is not a function of time, the two terms in this equation, the kinetic energy and the potential energy, are functions of time. So x is a function of time and the velocity is a function of time. But they work in unison with one another in such a way that their sum, this sum, is a constant. And if we plot this, so let's say the x-axis here is going to be m omega times the coordinate, and the y-coordinate here is going to be the momentum. So we see that this trajectory, basically in the phase space, describes the motion of a harmonic oscillator. It's a motion on a circle. And the radius of the circle is determined by the energy of our harmonic oscillator that we. And this motion is a phase portrait of this classical system. And by the way, I will just mention in passing that there is a relation between the phase portrait of classical system and the corresponding spectrum of quantum systems. But that's the only thing I'm going to say here in this regard. So now let us move closer to the main subject of today's lecture and make the oscillator quantum. So the motivations to do so are many, as I said. So for example, we can think about, instead of having a classical mass on a classical spring, we can talk about, let's say, a two-atom molecule and the oscillations of this molecule relative to the equilibrium position of the atoms at low energies. These oscillations are going to be described by a quantum harmonic oscillator. So of course there are many more examples, as I mentioned in the beginning of the lecture. Let me just mention another one. So for instance, if we're talking about the behavior of a quantum particle in a rather arbitrary potential v of x, so let's say something like this. So if we are interested in low energy behavior of the particles and we're near the minimum of the potential, we can always expand the potential v of x near the minimum, so it's going to be v of x naught, so this point, plus v prime of x naught x minus x naught, and this is 0 because this is the minimum, plus the second derivative over 2x minus x naught squared, and modulo this overall constant, which is just shifts the minimum of energy, and this shift of the equilibrium position, so the remaining part of this potential is really the quadratic potential that we have in the harmonic oscillator problem. So what I'm saying here is that you can almost always approximate a reasonable potential well near the minimum of the well with the harmonic oscillator, if you have a smooth function. Of course, if you have a square quantum well, we cannot do that, but in most cases you have a smooth potential, and in this case we can just replace it at low energies with this harmonic oscillator. So now let me erase this stuff and move further. So how to formally go from the classical harmonic oscillator in this potential to a quantum harmonic oscillator. So to do so, we have to pretty much do the following mathematical procedure. We can just put a hat here, and that's it. So that's how we make the oscillator quantum. So, well, seriously, what we have to do, we have to replace the energy of the oscillator. So the energy, remember, we derived in the previous slide for the classical harmonic oscillator. So now we replace the energy of the oscillator with the Hamiltonian, which is an operator, the momentum, which is just a variable in the classical description. Now we replace it with the operator that acts on the wave function. And in principle, we can put a hat also on top of the coordinate, although the action of the coordinate on a wave function in position space is pretty simple action. It's just a multiplication operator. But this pretty much what it means on the mathematical side to go from classical description with no operators involved to quantum description with operators involved. So this is the mapping. And the problem that we want to solve now is to find solutions to the eigenvalue problem. So of course it's a time-independent problem, so there is no time involved. And what we want to find a solution to this equation. So when solving this Schrödinger equation, and in particular when thinking about the allowed energy levels, so what we should keep in mind about this harmonic oscillator potential is one property that makes it very different from what we have seen before. Namely, that this potential the potential energy grows indefinitely to infinity as x becomes very large or very negative. So there is no room here for plane wave-like solutions propagating to infinity, and the only thing we may have here are discrete states corresponding to particles localized in the vicinity of this x equals 0. And to determine these energy levels, this harmonic oscillator spectrum is exactly the main problem we're going to be focusing on in the next couple of videos.